All right. So, bring this up. Sorry for delayed recording. I had to reboot to get the recording to work properly. All right. So for today, this is the last bit of fluid statics. All right. We want to consider what happens when a fluid is in an accelerating container or a fluid is in a rotating container. All right. So, and then if I think we'll have some time, we'll touch on the concept of control volume before we move on to the next chapter, which is on control volume, mass conservation, what else? Momentum and so on, momentum equation. Okay, so to start, let's start with something easy. Okay, if you have a fluid, all right, so this is the surface. Okay, you know G is 9.81 meter per second squared. All right, and we get pressure like this. So at the free surface, the pressure is constant. All right, normally. Okay, so P equals to P atmosphere. This is a line of equal pressure. Is that okay? Right or not? So it's called an isobar. Right, iso means same, bar, pressure. Okay, if you go down a little bit, the pressure increases, isn't it? P is equal to P atmosphere plus rho G H. Say this is H. Okay, and same height, same fluid connected, the pressures will be the same. So this is another line of another isobar. Say maybe here P equals to P ATM, here P equals to P1. Alright, so these are isobars. Is that clear? Lines of equal pressure, and you can draw many as you like. Alright, so each line across this line is the same pressure. Alright, and what's generating this pressure is G. Alright, if we were far away from Earth, let's say somewhere far away from the influence of gravity out there in the middle of space, alright, then there'll be no G. Then if you had a blob of fluid, it would just float around like this. It would stick together because of surface tension and so on. So unless you break it, it will stick together. All right. So the pressure is not too low so that it doesn't boil off, but it's a liquid. All right, not. All right, some liquid. All right, some blob of liquid floating around. If if on that far away place that we are, we want to feel at home, okay, so we would have to put this fluid in a container, all right, somehow get it in the container, and accelerate upwards. All right, not? Then your fluid will fill up here like this, and you get the same isobars and so on. Okay. Is that clear or not? All right. Okay? Yes or no? Right? So, the effect of G is equivalent to accelerating upwards at 9.81. Alright? No? Alright? So, doesn't mean gravity is pointing upwards. Gravity is pulling you down. But to give you that same acceleration, to give this water the same feeling, if this water was far away from Earth, no gravity, was to accelerate this container, accelerate up at 9.81. Okay or not? Then you have all this isobar. Okay? And your here, if this is H, here P equals to whatever atmosphere that you have in your spacecraft. Here is P1 equals to P atmosphere plus rho GH. And G here happens to be 9.81. Okay? But we can change that G. Alright? On Earth, we will always have this. Okay? But on the spacecraft, we can take that away and we can change it to whatever we want. Okay, so far? Alright? So, what happens if we are on Earth? Alright? Again, this is my analysis is slightly different from the one in the lecture notes. You can go through the lecture notes. Alright, my explanation a lot more physical meaning, hopefully. Alright, so if you are accelerating upwards, so we always look at the total acceleration. So this G is 9.81, alright, the effect of that acceleration. Let's say you take the container, you're on Earth now. Okay, the container is behaving the way it is because it's equivalent to the container accelerating upwards at 9.81. Is that okay? Then, if I accelerate even harder, I add. Maybe normally they call this in the Z direction, they call this in the X direction. AZ equals to, how fast you want to accelerate up? Let's say 5 meter per second square. Alright? So your total acceleration upwards is equal to 5 plus 4, 9 plus 14.81. Okay or not? Alright, so you just add vectorially. Alright, first you start with the, okay, so all our problems usually not in space, usually on Earth. So you start with acceleration upwards of the container of 9.81, and then you add vectorially whatever the acceleration is. Okay, so in this case, the acceleration upwards. So here P equals to P ATM. That one still changes. That one's still the same. Okay, but if you go down, previously we just multiply by 9.81. So here is P1. Alright, and isobar here. I can say P1 is equal to P atmosphere plus rho G, no, now it's not G anymore, 14.81 multiplied by H. Alright, this one here, this picture is G plus AZ. Okay or not? Alright? It's like sitting on a roller coaster or something like that. And you're accelerating upwards. When you're accelerating upwards, you feel heavier, isn't it? Alright? You feel as if the gravity is higher. Right or not? Okay, accelerating upwards at 5 meters per second square, I feel my gravity is higher. I feel my gravity is 14.81. Okay or not? Okay? In the other extreme, alright? So they normally term this in, remember you heard the term called G-force, alright, or G. So accelerator in terms of G, so if you want the acceleration is equal to positive because you're accelerating upwards, 14.81 divided by 9.81, and that's in terms of G. Okay, so it will be 1 point something G. Right? If you accelerate at 9.81, then it's equal to 2G because 9.81 plus 9.81 divided by 9.81 will give you 2. Right? So this is 1 point something. 1 point, I don't know, 5-ish. Approximately 1.5 G. Okay? Is that alright? So, the other extreme, alright? What happens? Okay, so we are on Earth, so G is always 9.81. Alright? Effect of gravity is equivalent to acceleration upwards to 9.81. And then example is like if you are in a lift and the cable breaks. Alright? Or sometimes the lift door open but the lift car is not there. Alright? Make sure you don't walk inside, but sometimes people do. Okay? So, in that case, your AZ is equal to minus 9.81. Okay or not? So your total is equal to, what's the total? 0. Alright? So by right, again here is P1. P1 is equal to P atmosphere plus rho 9.81 minus 9.81 H. Okay? So in that case, 0 gravity, all the pressure is equal. Alright? It's equal to P1. It's equal to P atmosphere. Alright? So anywhere you are, the pressure will be the same. Okay so far now? Any questions? Okay, now it's going to get a bit more difficult. What happens if you accelerate in the X direction? Okay? So if you accelerate the x direction, don't panic. All right. So again, your g is 9.81. You add your acceleration in the y, and you add your acceleration in the x. Okay. So your total acceleration is actually g is 9.81. The total acceleration is that way. Okay or not? Alright, so because your total acceleration is that way, do you expect the water level to be horizontal or not? No, it should be normal. So previously your acceleration this way, your water level normal. Now your acceleration, total acceleration that way, your water level normal. Okay? So whatever your vector, for your total acceleration, this one will be normal. Alright? Okay, so later we'll come out that one. So your lines of constant pressure will also be like this. Alright. Okay, now these are your isobars. Alright, so let's say we start here. We want to go down this way by a distance h1, and we go this way by distance h2. And I call this pressure at 1. Okay, so in this case, when you go down, your pressure goes up. When you go to the left, your pressure also goes up. Alright, because you have some, similarly, you have some component of acceleration in the x direction. So, P1 is equal to PATM plus rho G plus AY, rho G, H1 plus rho G plus, no G here, sorry, AX H2. Okay or not? Alright? So, similarly, like previously, when you go down, your pressure go up. Now that you have x acceleration that way, if you go against that, if you go in the direction against that acceleration, your pressure will go up. Okay or not? So if you go this way, your pressure go up by this amount. If you go this way, your pressure go up by this amount. Okay or not? Bring up. Any questions or not? Okay. So finally, if you want to work out the gradient or the slope, all right, no problem. All right, the slope is always 90 degrees. All right, so this angle and this angle is the same. Correct or not? This angle and this angle same. Correct or not? This angle is tan theta is equal to AX over AY plus 9.81. I got AY or AZ now? Yeah, mistake. So AZ now. AZ. Okay, so this angle you expect tan theta. Alright, so this height is equal to H1 over H2, say. Alright? You can expand further on the trigonometry and so on, but I presume you can do that. Okay or not? Any questions or not? You're alright, huh? Okay. Alright, so that's when you have a what do you call that? A container. Alright, what's the container doing? Accelerating. Alright? The net effect is just like rho GH, except your G is no longer just upwards, but upwards plus whichever direction the container wants to accelerate in. Okay, so you have a isobar. Alright? Okay. 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 Any questions? Okay. So now, the next, I'm going to take it one step further. What happens when a container is rotating? All right. You expect, intuitively, you expect that the water level will spin up like this, isn't it? Correct or not? All right. Okay. So, when the container is spinning, all right, this fluid, okay, this is the center line. This fluid parcel is going around in circle, isn't it? Okay. This fluid parcel at some distance r. What's its acceleration? Well, this fluid would still experience, if you have gravity, would still have experienced gravity here. So equivalent to G is equal to 9.81. Either gravity downwards or equivalent acceleration upwards. Okay. And it's also accelerating towards the center, isn't it? Okay. So this is again, the fluid is not really flowing. It's like a bulk fluid. All right. The whole thing is rotating. All right. It's example, you put a container on a lazy Susan and spin it around. Okay. You might have done that when you were younger. You still might do that. I don't know. Okay. So the acceleration here, AR is equal to, well, it depends on your sign convention, but normally it's negative because R is pointing outwards. You're accelerating inwards. So it's negative omega R squared. Is that correct? All right. Is that correct? Correct. Huh? What? Oh, omega squared on R. Okay? So that's your acceleration. All right? Okay now. So you expect as you go outwards, your pressure will increase because of this acceleration, the fluid accelerating inwards. The higher pressure on the outside needs to be there to push the fluid to make sure it goes round in a circle. Okay or not? All right? So there needs to be a force to push this fluid here, and that force is due to the higher pressure on the outside. Okay? All right now. R acceleration is R omega squared. Okay, acceleration I think is V squared on R, isn't it? All right. V squared is omega squared R squared on R. So it's cancel R omega squared. Okay. All right. Okay. Okay. All right. So let's calculate the pressure. All right. At some point here. All right. All right. So the pressure difference between point here and point here is P2. P1 is just some point in the center line is equal to here 2, here 1, P1. All right. Plus rho well, we normally use rho GH, but our G is R omega squared, and we can't just multiply by H, we have to dr it, integral from 0 to R. This distance is R. Okay? It's rho GH, all right, but our G is not constant because the rotational acceleration not constant. Okay or not? Alright? So we have to integrate, we have to sum up all the existing, cannot just multiply straight off. Okay? So it's equal to P1 plus rho omega squared constant, rho omega squared, R integral become R squared on 2. So R squared on 2, big R 0. Okay? So equal to P1 plus rho omega squared big R, R squared. Alright? On 2. Okay? So that is the pressure between the center and some point at 2. Okay? And if you want to go down, here not. Okay? If you're going in the vertical direction, then it's just equal to 9.81. So this one, let's say H, this distance between 0 and H, P1 is equal to P0 plus rho GH. Okay? So in this case, if you're going up and down, alright, you're only experiencing gravity in the Z direction. So go up and down, same like earlier case, rho GH. Only if you're going in and out, then your pressure changes given on this formula. Okay or not? Alright? Okay? And the pressure is always bigger on the outside because the fluid is accelerating inwards. Alright? When you're rotating, you're accelerating inwards. The pressure has to be higher on the outside to push you inwards. Does that make sense? Okay or not? Alright? So finally, if you want to find isobar, okay, so you expect the pressure, yeah, okay, you expect the fluid to like this. Why? Because the pressure here is higher than here. That's why the water can rise up. Alright? Okay, so here, and you expect the isobars to be like this also. Higher pressure here, lower pressure here. Alright? Okay? So if you want to equation for the surface, alright? So this is R direction. Okay? So you expect, just because your fluid is spinning, your atmospheric pressure is still the same. So at this free surface here, where it's exposed to the gas, the air, the pressure is the same. Alright? Okay, so the pressure, anyone at this point, pressure is equal to P atmosphere. Alright? Okay, so let's start at this point. Call this distance H. Alright, as you go out, alright, your pressure will increase. Alright. So pressure is atmospheric everywhere. Alright, is equal to starting at this point, P ATM plus rho omega squared R squared on 2. But I also go up minus rho GH. Alright? Okay? Alright? So, I repeat again. So, I start here, PATM. I go out. So, my pressure will be equal to PATM plus rho omega squared R squared on 2. Okay or not? So, I'm here. Here up to here. And I go up. And if I go up, my pressure drops by rho GH. Okay or not? Is that alright or not so far? Okay? So, and the pressure here is PATM. That's why it's equal to PT ATM. Alright? So, I repeat again. I start at this point, which is atmospheric pressure. I go out, so the pressure increases by rho omega squared R squared on 2. And I go up, my pressure decreases by rho GH. And finally, at this point, this is the isobar. Alright, the free surface, the pressure must be constant, and that pressure is atmospheric. Okay or not? Any questions? Alright, so in that case, this one will cancel off. rho omega squared r squared on 2 is equal to rho GH. Cancel, cancel. So I get H is equal to omega squared r squared on 2G. Alright? So this equation, alright, basically tells me the difference in height between the center and the edge, wherever I am. Okay or not? So, example, alright, let's say my container R is equal to, for my container, I have a radius of 0.2 meters, right? Not so big, but this size container. Okay, I'm rotating at 2 radians per second, alright? So if I put in the H is equal to omega squared 2 squared r squared 0.2 squared over 2 9.81 equals to how many meters? Someone punch that in the calculator. This will be my height difference between center and edge. Height difference of liquid. What's the answer? Okay, 8.15 mm. Right? Okay, so if I rotate, I expect height difference, and this height difference I can predict this way. Safe. Any questions or not? Huh? Okay, how did I get this minus rho GH? That's the question. Okay, so from here to here, my pressure is increasing as I go out. Okay, because the fluid is accelerating inwards. But I'm not going to this point only. I'm not stopping here. I'm going up. All right. When you go up, the pressure goes down by this amount. Right? Or if you want to go the other way, also can. All right. Let's say I start here. What's the pressure here? PATM. I go down plus rho GH, and I go inwards. If I go inwards, then minus rho omega squared r squared on 2, and then I'm finally here. What's the pressure here? PATM. Okay, same. Alright, you can go either way. This one, this equation, I started here, and I went up, out and went up. Here I went down and went in. Okay? Okay? It's negative because alright, it's because either you go down or here you're going inwards. You go inwards, your pressure goes less. Okay? Alright? Okay? If you stand in the eye of a storm, okay, example, if you're standing here and the storm going, you're standing in the eye of a storm, okay, pressure very low once. Alright? Okay. Well, we have to take this way, it's confusing. Any questions or not? Safe. Huh? Yeah. Yes. So normally, so by right, if you want, this one should be small r. All right. So the notation, all right. The notation is, I repeat again here. All right. I use the correct notation here. Small r is some arbitrary distance from between between the center and the edge. All right. Normally we put big R is the radius at some particular distance of our choice, and normally it's the edge or some point. So big R is one location. Small r is a variable that can vary between 0 to big R. All right. Big R is the final one. That's why when I integrate from 0. All right. I integrate from 0 to big R. D small r. Small r is a variable. Okay. Same here. Small r is the variable. So from some arbitrary distance r, the pressure is here. Okay. Yep. Yes. All the pressure on the same line is the same. Isobar is same. Okay. Okay. Any other questions? Okay. So we've completed fluid statics. All right. Any of you heard of what the control volume is? All right. Okay. Control volume and system. Okay. Let's start with one simple thing first. Everyone heard what a system is? Okay. A system is whatever we are interested in now. Okay. So if this block, all right, that's our system, all right. It doesn't disappear, it doesn't suddenly grow, so mass is conserved in the system, isn't it? All right. So you all heard of conservation of mass, isn't it? All right. So that's our system. We track it. In case our system breaks into two pieces, all right, we must still continue tracking those two pieces. That is our system. If our system breaks into 10 pieces, we must continue. You cannot lose any of those pieces. As long as you don't lose any pieces, your mass is conserved. Correct or not? All right? And you don't suddenly add more pieces to it. Okay? So that's our system. If our system is originally 10 pieces, and suddenly they join up to get one piece, all right, then that is the system. 10 piece, one piece is still our system. Mass is conserved. Okay or not? Or how many other pieces are? Okay. And same for the system. You heard F equals ma, isn't it? Yes or no? All right. That also applies to the system. All right. As long as the system stay together, you put a force, you can get acceleration. Mass, the mass of system conserved. All right. So mass doesn't change. If the system breaks into 10 pieces, same, this equation still applies, all right? But now you have to track all the different mass and acceleration, right? Because they may not move together, all right? But normally for your guys, I don't think normally it doesn't break up into too many pieces. So if it still stays one piece, that's the two equations, two things that we want to cover in our this next topic, all right? And for system, it's very easy, okay? But sometimes very hard to track the system. Okay, system moving here, moving there. Some parts disappear, and some new stuff come into our thing and all that. Okay, so in a continuous flows environment, very hard to track the system because some new stuff coming in, old stuff going out. If you want to follow the system, you'll be following the same parcel of fluid throughout. Okay, even though it has already come and gone, and still you are still following that same fluid. Very boring. All right, may not be very useful also. Okay, so that's why we come to the concept of control volume. Okay, control volume is an arbitrary box, arbitrary volume. All right, so control volume got two parts. It's just a volume, just a box. All right, it can be any shape, doesn't have to be a box. Okay, all right, control volume, arbitrary. All right, arbitrary volume. All right, normally they call the surfaces control surfaces. Okay, no? Okay, so we have a box. you have control surfaces, and this box can be stationary, can be moving, can be deforming, and can do all in one time. Okay? Example, let's see, I bring up the lecture slide. Sorry. Lecture slide. I think lecture 7. Alright? Let me bring up. Okay. So, alright. So, normally we would select, so this is arbitrary. Alright. So, normally we will select it around the thing of our interest. Alright. Example, okay. If you have a pipe, let's say, alright. If you track if you want to track the system, alright, so you mark a few particles, alright, you mark them. I don't know how you mark them. Okay? Alright? And then you follow. At some later time, they will be here. They're all deformed already. Okay? And at some later time, some may land down here, and some may land down here. Okay or not? That's your system. Alright? That's your system. And after that, they go up. Alright? But you're not, maybe you are interested in what's happening at this junction. Alright? You're not interested in so much tracking this little bit and going out there and so on. I'm interested in this junction. What happens here? How much goes in, how much comes out, and so on. Okay, let's say, for example, usually because sometimes it's okay, you want to follow the fluid particle all the way thing, but a lot of times you want to know what's happening at a particular location. Alright, what's happening for this thing, what's happening there. Okay, so the tool, alright, we cannot just follow the system, follow a track, a fixed blob of fluid. We need to follow, we put a box around what we want to look at. Okay, so as I said, the box can be, the box can be, alright, for example, aeroplane, alright, you want to study the performance of the engine, okay, so we put a control volume around the engine, alright, but the engine follows the aeroplane in the ideal situation, alright, so the engine follows the aeroplane, so our control volume had to follow the aeroplane, okay, so it's moving with the aeroplane, alright. Sometimes we're interested in a balloon, okay, as the air comes out of the balloon gets smaller, alright, so our control volume will have to match the size of the balloon at any given time, alright. So in that case, then we will only know that based on this control volume, air only enters and out through this hole here, okay. So example is also, let's say you want to track what's happening with your lungs, okay. When you breathe, your lungs expand, contract, and so on. Alright, so you draw a control volume, that control volume will also have to follow the geometry of your lungs. Okay or not? If it's a fix, then you have things crossing over. Okay? So, alright. So, any questions here before I move to the next piece? Okay or not? Alright, so that's our control volume. Things can only go in and out of the control volume through the control surface. Alright, it cannot suddenly magically disappear here and appear inside. Normally that doesn't happen. So it has to go through the control surfaces. Alright, that's why we talk about the control surface. Alright. So, now let's, okay, for those who like a lot of, alright, there's this overall theory that links control volume with system, and that's called the Reynolds transport theorem. All right. There's a section in your textbook. All right. You can read it if you want. All right. I think it is covered a lot more in your third year. For those doing mechanical engineering, it's in fluids too. For those who are doing chemical engineering, I think it's in heat and mass transfer or something like that. Right? It's there lah. All right. It's the overall, but here we'll do a more kindergarten approach. Okay. This one is like a grand theory for the whole thing. All right. We won't talk about grand theory. We'll do a more kindergarten approach. Okay. So our control volume must conserve or not? No. All right. Must not really conserve in our control volume. All right. So mass is conserved in the system. All right. But basically, the mass in control volume can go up and down, correct or not? Because it's just arbitrary box. All right. If I have a box, all right, or not even a box, I mean imaginary box. So it's not even a physical box. It's only imaginary box. There's no box there. Okay. And suddenly a mouse runs inside my imaginary box. Then my imaginary box will be heavier by, how heavy is the mouse? 1 kg. Okay. Wow, very heavy mouse. All right. I think in some parts of Africa, got mouse big one. Africa, South America, I think. All right, but they're different idea. All right. So they got big ones. But anyway, okay. So mass not conserved. Suddenly, my arbitrary thing, all right, we got just air, maybe weigh only 5 grams. Okay. Suddenly a mouse ran into that region. Now my volume of air, 5 grams plus 1 kilogram of mouse, 1.05 kilogram. So mass in control volume, all right. So rate of change of mass in the control volume, all right. So plus mass rate of change. So if your rate of change is positive, means your mass is increasing. All right. If this one increase positive, mass entering. This is positive. This positive cannot be zero here. All right. So minus mass entering plus mass leaving. Rate put rate of mass entering, rate of mass leaving equals to 0. Okay, that's mass conservation for control volume. All right. If the rate of change of mass in the control volume increases, so this you get a positive here. All right. Or if you want, maybe make it this way, equals this one minus this one. All right. Normally they like to put it all one side, but physically explanation a bit easier. So if the rate of mass in the control volume, the rate of change, all right, if you have a positive rate of change, means your mass have increased. All right, rate of mass entering minus rate of mass leaving. Okay. So in terms here, mass in the control volume, let's just call that density. Integral of density dV, right? Or in terms is just density, and we want the rate of change of that. All right. All right. Rate of change of mass. Mass is density times volume, correct or not? But in case they're not all the same density, so that you just integrate. So density times a small volume, and you add up all that volume to get the total volume. All right. I know some of you haven't done maths A yet, so it's a bit all the volume integral, but I'll keep it simple. All right. But it's equal to density times volume. All right. Add up, sum it up. Alright, or you don't like this, sum of density times delta times the volume. Okay, you sum up all the volume. This equal to mass entering the control surface. So this normally we term rate of mass entering m dot in minus m dot out. Okay, not m dot is equal to rho m dot well here this one I need to detract a little bit. Okay, m dot is equal to mass is equal to rho times volume. Alright, so if you to move that mass, density times volume. Alright, so m dot is equal to density times the volumetric flow rate. Alright, v dot. Alright, volume is like say liters per second. Okay, that's your volume. Alright, and that volumetric flow rate is equal to times area times velocity. Okay, so this one very stunned. Okay, alright, so if you have a particular area, this is small d. Alright, okay, alright, so previously this was your volume. Okay or not? Alright, so this is L, say, so your volume is equal to A times L. I know. So in 1 second, if so, let's say, okay, so your volume A, this say this is 3 meters. So your volume is 3 times A. Okay, now. So if in 1 second, if this volume moves across some arbitrary surface, okay, so it's moving at 3 meters per second, correct or not? Alright, 3 meters per second. So your volumetric flow rate, volume, okay, so I repeat again, so we have a volume, the volume is 3 meters, area length is 3 meters, area A. So the volume is 3 times A. Alright, so if this amount passes our control surface, passes certain surface, so let's say this is the surface here, okay, if at any given time, alright, in 1 second, 3 meters of this, think of this like one very long spaghetti, okay, at any given, so the cross section of the spaghetti is A, if that spaghetti moves at 3 meters per second, in 1 second you will have 3 times A volume going in, correct or not? Alright, so that's why the volumetric flow rate is equal to the area times the velocity. Alright, because area times the velocity is the length of at how much you move in 1 second. That's the velocity. Okay, alright, so this is m dot out in minus m dot out. Okay, so it's actually rho A V in minus rho A V out. Okay, but we're not going to, in case your velocity not all uniform, alright, so that one you give you rho V in dA integral minus rho V out dA integral. Alright, in case they're not all same, then you must integrate the entire area. Alright, that's what the integral is. Which is basically sum of, in case you got not only one spaghetti stream, you got many spaghetti streams. Alright, each of the spaghetti streams not moving at the same speed. Okay, so you need to integrate that. Alright, but if you have only one spaghetti stream going in and one spaghetti stream coming out, then it's like this. Alright, one tube or whatever, one. Okay, I think I'll stop here. Next class coming in. Alright, so we'll continue to Thursday. Okay. I'll meet you outside for those who want my signature for attendance sheet and so on. Okay, right. Okay, and put the huh?
Number 7 tutorial 1. The